Hello, everyone. Welcome to the Nomads Podcast. I'm your co host Prachi.
And I'm your co-host Bhavya.
Most of what we know about the universe actually comes from what we can't see. Only a tiny fraction of the cosmos is made of normal matter, the stuff that makes up stars, planets, and us. The rest is a combination of what we call dark matter and dark energy, which, although invisible to our telescopes, is absolutely crucial for how the universe expands and how structures form over billions of years. So, how do we even study something that we cannot see? One of the most powerful tools we have is weak gravitational lensing. As light from distant galaxies travels through the cosmic web, the gravity of dark matter gently stretches and shears those galaxy images. The effect on any single galaxy is tiny, almost imperceptible. But when you measure this across millions or even billions of galaxies, a pattern emerges. A subtle cosmic fingerprint that tells us how matter is distributed and how fast the universe is expanding. This is what our guest today, Dr. Niko Šarčević, works on. She's a cosmologist working at the intersection of data and theory. Niko is part of the LSST Dark Energy Science Collaboration, and her work focuses on understanding and modeling the systematics that can bias our measurements. Things like how galaxies are intrinsically aligned, how we infer their redshift distributions, and how all of that feeds into weak lensing and dark energy constraints. So if you've ever wondered how we really know that dark energy exists, or what kinds of experiments are used to learn about this invisible matter, you're going to be thrilled. So with that, let's go.
Dr. Niko Šarčević, welcome to the Nomads Podcast.
Thank you for having me.
So, dark energy and dark matter has been troubling cosmologists, astrophysicists for decades now. Despite a remarkable progress in precision measurements and things that we can detect in our labs, we still haven't been able to pin everything down, understand what characterizes dark matter and what's the true nature of dark energy. So why don't you start by explaining what these two things are? Well, that's going to solve the whole thing. but also maybe talk about what we don't understand them, despite, and I repeat, despite the remarkable progress in the field.
Well, it is a very big. This question is actually takes a lot of hours and days to explain, but let's try to explain it in very simple terms. So if you think of the universe as a whole, and it's made up of some ingredients, it's the same way you can think about it as I usually use ramen bowl as an example. If the whole universe is a ramen bowl, then you have different ingredients in there, right? So what we know now, at this point in 2025, the universe consists of several components. The one that is taking up the most, the largest fraction, is dark energy component. Then we have dark matter, and then the rest. The rest being a very small amount of normal matter, baryonic matter, and I usually try to explain it. It's just like normal matter, meaning the matter that I'm made of, and this microphone, and this blackboard, and your umbrella at home, this is just normal baryonic matter. The difference between, how would I explain the difference between dark energy and dark matter? There are two components that have different equations of state.
Right.
I think that is the most correct answer that you
Okay.
can have. But the nature is very different. Now you can tackle the problem phenomenologically, which is not actually the job of a cosmologist in a way. It's more for people in particle physics. Whereas in the line of work that I do, you can try to infer the nature of dark energy, dark matter, but in a very different way, in a very different approach. And in most times, what we can provide is the answer of how much approximately there is dark energy or dark matter in the universe.
Right.
But depends on, of course, the technique or the probe you're using to tackle the question. So cosmology is a field where I work in, has a very different approach rather than something I worked on before, which is the dark energy experiment, dark matter experiment, where they are trying to detect dark matter in a very specific model.
Right.
So you see just the approach is very different.
Right.
I hope this is a
Yeah,
very trivial
for
way
sure.
of
So
explaining.
what I understand about dark energy is like it's also attributed to the acceleration of the universe. How true, and what do you have to say about that?
How it is related? Well, you can relate it very easily if you go down to the nitty-gritty and just write down the equations. You can, the Friedman equations or the Einstein-Will equations. You can get to the relationship that the dark energy is a component that is driving the expansion of the universe. So
Right.
think about it that way.
So if, my understanding would be, so if I say that dark energy, if it's just the Einstein's cosmological constant, then where does the problem of fine-tuning come from? Like, how do you think about that?
Fine-tuning problem is not my area of expertise. It is a job of theoretical physicists. So I'm going to step away calmly from that question. Okay. But fine-tuning is, the way I understand it, is also comes with all of these problems. Like it's also in a way a philosophical problem, but the naturalness and other things. And I think you can talk to Cliff Burgess about this and other people that would provide much better answers than I can.
For sure. So talk about your, what exactly do you do? What's your area of expertise?
Of course.
And what do you work on?
Gladly. Okay, so what I work on is let's try to go from bigger scales to smaller scales. So if you think about physics, and physics has many subfields, one of them being astronomy, and then which is the science of celestial bodies. But then this whole field within astronomy, I think, is called cosmology, and that is a field of physics that studies universe as a whole. And I know sometimes it's hard to comprehend, but it is absolutely amazing and fantastic that we are actually able to do that. The whole thing, like to describe the whole thing with actually very simple equations.
Right.
So the field has been we've been doing this for many years. Now within cosmology, of course, there's many fields. What I do in particular is late time cosmology.
Okay.
And what I mean by that is, if you think about cosmology as a field, or the universe, you can study universe in different evolutionary stages. So you can have people who are only concerned with early times, meaning Big Bang and CMB studies. CMB being the cosmic microwave background, just to be sure to people to understand. Yes. Yeah. You can also study some intermediate times. This is dark times. There are people who are coming up with very interesting techniques to try to tackle this problem, because it's very difficult to observe. And then you get to a stage of universe that is currently in, where we have fully developed, evolved galaxies.
Right.
So you can also study cosmology, do cosmology, study the universe as a whole by observing universe as it is now, meaning observing galaxies. In particular, so you can do many things. There's a technique that I work on, it's called weak cleansing, and that is a technique or a method where you observe the distribution of galaxies, meaning the positions of the galaxies and the shapes of the galaxies, and but you have to have a large sample of galaxies, meaning you can't really just observe one galaxy. You need to have a large sample, meaning millions and billions of galaxies. And then by studying their positions and the shapes, you can infer exactly the cosmological parameters which tell you how much dark matter there is, or dark energy, and so on.
Okay.
Right.
Now, you can do cosmology by studying other things. For example, we have a large group here at Duke, led by Dan Skolnick, who's pretty famous in the field.
Right.
And they're doing supernovae, so they are observing a lot samples of supernovae, and then actually doing studies and inferring. It says a lot about determining the H naught, the Hubble parameter. So there's a horde of PhDs and undergrads here who are working with Dan on that. But this is doing basically astrophysics, but in terms of cosmology. Right, it's a cosmology study, but you still need to do a lot of astrophysics, which we will come to that at some point. But now in this precision cosmology, we are also actually doing astrophysics with cosmology in a way. I will explain that later.
Right. So you mentioned a couple of questions. First is late time basically means relative to the early universe, and late time essentially just means this.
Now,
right?
Yes.
Okay, right. And could you also explain what weak lensing is and how is it different from strong lensing? What is lensing for people in the audience who don't know?
Of course.
Yeah.
So it is very easy for people to see, but the point is you can do the tests at home. You can take a wine glass and a light source. It can be like a lamp or a candle, and you can point the bottom of the glass and look at the candle through the bottom, and you will see that the light of the candle or your light bulb is going to be like stretched through that. And this is because it's a simple lensing effect, where your light of your source, in this case it's a candle, is passing through a lens, and then you have the lensing effect. Now, people, when we had the nice images from Hubble, for example, or later now with James Webb Telescope, people saw this, the image, some objects or artifacts on the images were curved, and realized this is due to lensing. And it happens because between the source of light, which is some galaxy that is very far away, so between that galaxy and us, there exists a large mass between, and the mass is curving the space-time, because light, when we say universe is flat, what we mean by that is if we shoot two light rays, they will always travel parallel. Right. That means flat universe.
Yeah.
However, if there is a large mass on the way, on the trajectory, you will have a bending, right? Because the light follows the geodesic.
Yeah.
Yes.
Right.
So the lensing is coming due to that fact that there is a large mass between us and the light source.
Right.
Right.
And now the tricky part is there's this effect. You can have the stretching of the image and the magnification.
Okay.
So these images, when you see like the Einstein cross, there's like these effects called the Einstein cross and so on. This is called strong lensing. So it has two limits, or like three, there's an intermediate, but mostly strong and weak lensing. Gravitational, I should say that obviously it's gravitational lensing question. And, excuse me, strong lensing you can see by eye, and you can do it in like one galaxy, right? So you are actually, the stretched image of a galaxy is the image of a galaxy that's behind this cluster that's between us and the said source. Weak lensing you can't really see by eye. And it's a very subtle effect, and what it happens is that if you start with the cosmological principle, which we know it holds, and cosmological principle is a statement that the universe, it's based on observation, obviously. It's not a theory. It's based on observation.
Right.
What this data is telling us, that the universe is very homogeneous and isotropic on large scales. So on small scales, that is not true. Of course, if you look at the solar system, you have this gigantic sun, for example, in the center, and then these tiny planets. So it's really not homogeneous, right? Because the mass is centered in the sun. But as you zoom out outside of the solar system, and at about 100 megaparsec scale, the universe becomes very homogeneous and isotropic. That means that that looks pretty much the same wherever you look in every direction.
Right.
So, and this now drives a lot of interesting statistics into it, because when we have something that's very random, we know it's our beloved Gaussian distribution, right? So it's very Gaussian, it's very, very simple on large scales.
Right.
So you take that into account and say, okay, it looks like it's pretty much the same wherever I look, in every direction. Cool. That means that the galaxies, the orientation and the shapes of the galaxies are pretty much random, right? So you can take statistically, you count and you measure this orientation or the shapes of the galaxies everywhere where your survey is covering. And it should, if you sum them all up, they should average out, meaning it should be zero. However, if it's not, then you can get the amount of matter that is doing or changing the shape because of the lensing effect, the weak lensing.
Right.
So this is the technique.
Interesting.
It's a very subtle, very small effect, but you can use it to infer how much of matter is there between us and the galaxies that you're sampling. But it has to be a large sample of galaxies.
Yes.
I see.
And then you extrapolate, okay, there's so much matter here, you can say approximately. But it's very, actually, it can be very precise or
So-
accurate measuring,
Are there any constraints on the mass? So it's like, so what I mean is that the same mass would also cause strong and weak lensing, or is it like a different object that this phenomenon relates to?
In strong lensing, you need to have the positional, right? It's a geometrical question.
Right.
So you have to, like, this galaxy and the cluster have to be in a very nicely aligned way where you look at it from a certain angle. It's the same, I don't know if you ever talk to people who work in a field called AGN, active galactic nuclei.
No.
So active galactic nuclei are objects, basically, the centers of active galaxies, meaning that there is a black hole that is active.
Right, okay.
Yeah, and then it can have jets, but if you go into the morphology and classification, they have a lot of if I remember, I mean, I don't work in this, I remember from when I was a student, but there's like Seifert 1 and Seifert 2 galaxies and or AGNs, and then they have, what's that they called, BLX, and it is an insane amount of names, but it's the same object, it's just, it matters if it's like aligned towards you, if the jet is shooting at you, those are the BLX, if I remember, and but it's the same idea of the object, right? The same definition, it's just the position. So in terms, going back to strong lensing, there is a critical mass. Of course, it depends on the mass, but mostly it's a geometrical thing, right?
Oh, okay, I see. So you also mentioned about cosmic microwave background.
Yes.
Which is another cornerstone of modern cosmology.
Absolutely.
So, and our former podcast guest Eve talked about how we can use that to study the evolution of the universe. So how is studying that different from studying through weak lensing?
Okay, so this is a very good question. The questions that we are trying to answer are more or less the same when you break it down, right? It's basically the question, what you started with, what you opened this podcast with, what about the dark matter, dark energy? How are we going to tackle this? So it's basically like any problem in life or whatever you have to do, you can tackle it from different ways, right? If you, for example, you need to clean your bathroom, you can go about it different ways. You can first take everything out and clean, or you can, start with one, right? You can hire someone. It is very different techniques to do the same thing. So in terms of physics or cosmology, first of all, it is, the time, the evolutionary stage of the universe we are looking at is different. So different physics might be in place. That's one thing to keep in mind. I mean, there's many things to keep in mind, but this is one of the major ones. But the object of, or the observable is different.
Uh-huh.
So you can do physics, you can, instead of doing, saying like classifying cosmology, we can do late time cosmology or early time cosmology. You can also say, you can classify it by the observable. So what they are looking at usually in CMB is the photons of the cosmic microwave background,
Okay.
whereas we're looking at photons of the galaxies. So it's two very different things.
Right.
You can do cosmology with gravitational waves, what they're doing now, right? You observe gravitational waves and then you put it in some cosmological context.
Right.
The supernova people, they're observing the light curves of the supernovae,
Right.
which is a different object,
Yeah.
but interpreting it within the context of cosmology, trying to answer these questions. So that's one of the things. And then of course the whole machinery behind how you actually measure, and this is why you have different experiments that are built. It's completely different. It's a completely different science in a way, but not really, because we are trying to answer different questions, the same question but with different techniques.
Got it.
I don't know if this explained it
No,
to you.
it did, in fact.
Maybe if you could talk a little bit more
Of course.
about gravitational wave analysis and so on. It may or may not be your area of expertise, but like my question is fairly general, which is, after this remarkable discovery of gravitational waves, why are we still looking for electromagnetic signatures and so on? Why are we still looking at photons? Or is there a bound, or do they just look at different things?
Well, first of all, to do any meaningful science, and I'm just not talking about physics, I mean every science, including medical sciences, you need a large sample, right? You can't.
Okay,
Right.
that is nice.
That's first and foremost. Secondly, gravitational waves are not as abundant,
Right.
at least in terms of how we are, how many we detect a year or in a month, compared to all the photons that we
That-
have.
Right. No, that's right. I see.
So the photons are the oldest and the most beloved, I think. Of course, you can do particle physics, you can do cosmology with particle physics, study the showers or of particles, the cosmic rays, I mean. But it is very important to keep doing all of the spectra and all of the observables,
Right.
because it is different pieces of the same puzzle. So getting the electromagnetic counterpart is absolutely crucial to the gravitational wave, because it is easier to interpret or to have a clearer picture when you have more words in a sentence, right? Otherwise, it's just, if you think of, getting a meaning in like getting one sentence and equating that with science, like, or some scientific, not discovery, but scientific truth, each of the photons will give you a few words and then gravitational waves, but then you need to make up what is the true sentence.
Right, okay.
So all these different areas just give you like different pieces of the puzzle.
Different pieces of the puzzle,
And
think
then
about
you-
it. So it's absolutely important to have everything and have all the experiments that we can wish
No,
for.
100%. I agree with you. Absolutely.
But are there any experiments that are actively working on getting gravitational waves from galaxy as a whole instead of just black holes and neutron stars? Because if I remember correctly, most of the gravitational waves that we have observed, and those who've just been public, they're only for black holes and neutron stars.
I am not sure, actually. I think I saw the other day they published a map. It was on Twitter. It was shared at like LIGO, Virgo.
Yeah.
It looks very nice, but you see, it's like.
Yes, exactly. Yeah.
Right.
You can count it by. I don't know the answer to that. I'm not active in that field,
That's
but I could recommend you people if you want to talk to them.
No, that's great. That's good. So, in your area of research, late time cosmologists, what's one observation that you're waiting for, or will it be a smoking gun for something, and what would be the implications and consequences of that?
Well, I think it is not really. I'm talking of me personally. I'm not speaking in front of any collaboration or anything. For me personally, it's not so much the final goal. It's the journey that matters. And
Interesting.
to me, it is more fascinating the techniques you develop,
Uh-huh.
the methods, how to get to the answer, rather than, you know, getting to, when you get to the result that is already,
That's
like
it.
you already, you know, went through all of the pain, and then, you know, so I think what I'm really, I know what I'm really looking forward to is, well, several things. First of all, I do work for LSST. Under LSST, I work for Dark Energy Science Collaboration Desk, where I co-lead a forecasting group. And I am also part of the NASA Roman Space Telescope, which is going to be launched next year.
Yes.
Yes.
This is very exciting.
Oh, next year. I thought it was
Yes, next year.
2027 or something.
No, next
It's
year.
next year.
Oh,
Next year.
wow, okay.
And I'm external collaborator on some other experiments. But I am very much looking forward to the data from both telescope, because I don't know if whoever is listening to this, Vera Rubin Observatory, so the LSST, the telescope that is in Chile, it's a ground-based telescope. It's a very powerful machine, and I hope you all saw the images that we revealed in
Yeah.
June.
Yes.
There was it's stunning. It
Yeah,
is
beautiful images. Yeah.
it is better than Hubble,
Yeah.
Right.
but it's a ground-based. It's fantastic.
Yes.
I do love the Hubble. Hubble is still my favorite, I have to say. And then Roman is going to be launched. It's going to be a space telescope. And what I'm really, really looking forward to, and I'm working on it myself, is combining the data.
Okay.
There we go.
And this is one of the things that we are now really keen on doing. And what we can do in cosmology is, it actually follows up on one of the questions you recently asked me, is we can actually combine different experiments.
Oh,
wow.
okay.
Okay.
Yeah, so there is not only in cleansing, but we can, that is, there is a possibility, and people are combining probes.
Oh, okay.
So you can, and we do have projects with that, where we are combining the data, for example, or we do the weak cleansing stuff, excuse me, and we combine it with CMB and supernova.
Oh, wow.
You can do it. It's very difficult. It's very
Right.
difficult. It's not trivial, but it can be done. And actually what you get is, what we usually get as a result, is like the main plot of every paper in cosmology is this triangle plot, where we show the constraints on parameters, and the larger this ellipse is, the worse it is, but you get to shrink it, and when you combine the data, really shrinks it, because each of the experiment has its flaws, and it's, you know, it is stronger. I don't know, like weak cleansing, it can constrain this parameter really well, but lacks in we can't do, I don't know, like omega baryons as good as CMB can do. So you combine best of both worlds in a way.
Oh, that's
But it is a very
interesting.
difficult technique to do, because you can have several ways of going about it. But yeah, this is what I'm really looking forward to, and we have some ideas. I'm not going to tell about it because we are still testing it.
Okay,
But we had an
That's
idea
fair.
recently to
That is
try
absolutely
something out.
fair.
Yeah.
Yeah. So talking about the collaborations and the experiments, could you walk us through what exactly happens in these experiments, the desk and the NASA Roman? Yeah.
Well, first of all, what is really cool is that you get to work with a lot of very smart and cool people. And I am personally, I would never be able to just work on my own. I like working with people and really learning from, because everyone has, you know, is talented for something.
Yes.
So I think that the community in astronomy that we have, especially like in collaborations like DESC, and now Roman is still young, is really welcoming, and it really helps you evolve as a scientist, because everyone is working on the same thing. There is no distinction between, you know, who's in academic rank, because everyone is just working towards the same goal.
Right.
Yes.
Right.
Wow.
And if the collaborations like DESC, setting DESC as an example, because I've been working in DESC for the longest, it is the most welcoming collaboration is feel so. I really, really love desk, and the policies are really like you feel protected, you feel valued.
Oh, that's nice.
People push you and promote you, which I mean it helps, right? Because finding a job in this field is very difficult.
Yeah.
So desk is amazing, and now we're trying to do the same in Roman, where we are, fostering really it's collaborative environment where we are just trying to, work towards the same goal.
Right. So is desk shutting down, or is it like?
No. Desk is so the way you have to think about this is that LSST is this big corporation. Then you have the Rubin side, that's how we call it in jargon. Rubin side is the telescope itself, and I personally never saw the telescope, or I don't touch it, I don't know anything about, anything, I don't know about it. There are a few people here, is one of the PhDs that I work with, she worked on the instrumentation, but now she's moving towards, doing the data analysis with me. And then there's one professor here who also worked on the summit. But so there's this part of LSST, and then there's several collaborations that will be handling the data from LSST, right, from the telescope. And I think there is 6 or 7. I have to look it up.
Yeah, no.
But each collaboration is in charge of different science.
Right.
So there is like exoplanets and, like asteroids, people, I don't know, like probably some astrophysics, the galaxies. And then there's desk who is going to be doing cosmology. Because first the data is going to only come to us.
Okay.
But then at some point we will make it public.
Yes, I see.
Yeah. So, and then the way it works, when you look at desk as a collaboration, of course it has a proper structure like any organization should, with policies and everything. So you have the people, like the editorial board, it has the spokesperson, of course, who is elected every 2 years.
Right.
It's very democratic, it is rotated, so it's not like one person constantly.
That's nice.
It's refreshed, it's very important, although so far all of the spokespeople were fantastic. I have to say, we only now switched in July when we were in Urbana-Champaign for the collaboration meeting.
I see.
And then you have the big analysis group. We have the calibration people. I don't know that part. And then within the analysis group, you have many groups. People who work on something called photometric redshifts.
Okay.
You have people who work on modeling combined probes and their weak cleansing. There's a lot of code and infrastructure, of course, that goes into that. And then each of these groups have the leads,
Okay.
right?
Okay.
One or two, usually it's 2 people who are leading the groups, and I lead one of the groups that is in charge of forecasting, meaning that's a very cool thing which you can do. I mean, not in just cosmology, in general, in science, but we do it a lot. You can predict or forecast how well you're going to be able to constrain, in our case, constrain the cosmological parameters.
Okay.
Without any data. I mean, you just make it theoretical, synthetic data, right? You emulate what you're going to have, and you can see what you need to adjust.
Right, okay.
Another thing that we can talk about later is the blinded analysis cosmology, which is very important. But let's talk, I don't know if you have more questions about
No, we can talk
the
about that.
Yeah.
Well, the data, as I said, the data comes to us.
Before you do,
Sure.
one quick question. Can you briefly also elaborate on what are these cosmological parameters? What parameters?
Cosmological parameters, well,
Yeah.
of course, every ingredient, what I mentioned at the beginning of the podcast, so what you started with is dark energy, dark
Right.
matter, you can assign a parameter to each of the components, and that parameter actually gives you a fraction or percentage. That literally what it means. It doesn't have a unit, which we really like in physics, right? It just gives you, I don't know, omega matter, 0.3 or something. That means 30%,
Right.
right? 0.7.
Yeah.
So the parameters in question, you can then assign each of them. You can have the omega matter, just the dark matter. You can split them into, right? If you equate what is matter, right? It consists of baryons and
Right.
dark matter. Of course, this is all under assumption of which model we're talking about.
Right, yes.
If we assume the I like the lambda CDM
Yeah.
still.
Yeah, I was going to ask. So all these parameters are tied by some model of
course,
cosmology,
of course.
which is lambda CDM in this
Yes, yes, the flat lambda CDM.
case. Yeah.
So you will have then flat means it's connected to the shape of or the geometry of the universe. So you have the kappa or the k, not the kappa, sorry, the k, omega k, which is assumed to be flat. You have the matter, you have the dark energy component, and then of course you have other parameters, because this is just the cosmology part, right? You can have a small h or big H, whichever you want. Small h is just the big H divided by 100 h, right? But so the expansion parameter, you can have. If you do CMB, you can have the optical depth and other things that are relevant to them that also come into the model, because these triangle plots that I mentioned, they can get very big and very scary the more models you want to include. So you have to have a trade-off, which systematics I'm going to include, and that's one of the biggest things we should talk about definitely, which are the systematics, because you can assume just cosmology, no systematic effects whatsoever, and be very happy, but that's not the reality. And I think at some point in this podcast I mentioned, I don't know if you're going to cut it out, but I mentioned astrophysics, that we are now doing astrophysics with cosmology, and what I meant by that is that the upcoming surveys, or the surveys that's already taking the data, like LSST or Euclid, DAISY now, or what we're going to have, Roman next year. These instruments are so fantastic. I mean, you saw the images of LSST. It is outstanding.
Yeah.
But now we are in this problem where suddenly the universe on smaller scales matter.
Right, yeah.
So if you remember, I mentioned the Gaussian, right? Everything is nice and right.
Following the bell curve.
Yeah. However, the smaller scales, and we want to probe the small scales. When I mean small scale, so that's like in physical space, but also in the Fourier space. This is where the nonlinear physics comes to bite you back, and this to model is very difficult.
Of course.
So your picture of the universe or the result will depend greatly on which model you assume, underlying model, and how you're tackling your systematic effects.
Got it.
I see.
So that's why you can start off with your triangle plot, only having few parameters of cosmology, but then the reality is not so great, right? It's also, if you think about it, it looks very nice, and it's like, I don't know, a picture with very nice lighting, right? Image looks very nice, but once you start zooming in, you see every pore, and maybe I have a hair here, right? But this is exactly that, right? You need to be able to explain that. So we are zooming in, and why do we want small scales? First of all, we like weird physics. Who doesn't, right? I mean, you work in QCD, right? So you like weird physics. Secondly, if we cannot handle the small scales, we need to remove that data.
Okay.
We need to simply cut it out of the sample. And at the beginning or some point in the podcast, I think I mentioned it several times, we need large samples.
Yes.
Because this is very much a statistics thing.
Right.
And the more, the better. So, but as I say, to model these effects is extremely difficult, because there are tiny, tiny little effects that are creeping up. For example, if you remember, I told you that in weak cleansing you have the shapes, right?
Yeah.
And then you are using the shapes of the galaxies and the positions in order to tackle, to infer how much dark matter and dark energy there is. However, if a cluster of galaxies is in which they are, right, bound in a they're sitting. I'm using this term loosely, sitting in the same gravitational potential. They will not be randomly aligned.
Okay.
And they will be intrinsically aligned, because they tend to align in a certain way.
Right.
Mm-hmm.
I see.
And that is an even subtler effect on top of already a subtle effect of
I see.
cleansing. So there is a whole horde of physicists who work on intrinsic alignments, which this is how we call this.
Mm-hmm.
And actually I work on it, and in 2 or 3 weeks we're going to have international workshop here at Duke
Nice.
that will work on intrinsic alignments.
Oh.
Interesting. So these, maybe this is a naive question. So when in late time cosmology, when you're only probing large scale structures of the universe, how do these small scale effects creep in? Is the detector sensitive to it, or?
No, it's more like, so there's several stages of how you analyze your data.
Mhm.
The calibration and all of these effects is done before people like me get the data.
Mm-hmm.
So there's a lot of people who are very good at their job, and they know all the nitty-gritty stuff about the CCD and the camera and the imaging and cleaning up this. I don't know how to do that.
I see.
No, this effect is we call it. It belongs in a category of astrophysical systematics.
Okay.
So it's all of the physics we don't understand.
Mm-hmm.
I mean, we have some idea how it is, but you need, in the end, a very nice equation that explains it and predicts it.
Mm.
So some of the things is this intrinsic alignment, right? It will creep up because what we observe, I will get to that. I was thinking how to explain it better. So I'm going to first maybe start how we actually do this week cleansing, how the science is actually done. And maybe I will try to draw it on the table.
Yeah, sure. For sure.
Right, just think about, you have a lot of galaxies on your sky, right? This is the sky, and then you observe this patch with your telescope, and you count. What you get is a catalog from people who calibrated everything and cleaned up the images. You get a catalog of these galaxies. And what you can get is the positions of them.
Okay.
So that means raw deck, meaning where they are on the map of the sky, right? The raw deck, the right ascension and declination, sorry. Just think about it as XY position, right? Where it is on the sky.
Okay.
Another key thing you need, and it's very, very difficult to determine, is the distance to this galaxy. So every galaxy needs to have assigned distance, which we in cosmology, we call it redshift.
Right.
And then if you're very lucky, like in experiments like LSST, which you can get a shape catalog, that means the shape of the galaxy. So what we do is we measure a 2-point correlation function
Okay.
for the whole sample. So that means, what is the probability, if I have a galaxy here, what is the probability I'm going to have a galaxy there? And you do for all the pairs. So you do pairwise all of the counting, and you get, when you do a Fourier transform of the 2-point correlation function, that's power spectrum,
Yes.
and which we all love in physics,
Right.
So that's your observable. Or you can do the full matter power spectrum, or you can do the angular power spectrum, which we usually use the CLs. So it's just in a different space, in the L space.
I see.
So what you can do, you can correlate the position of the galaxies, and that's called galaxy clustering probe. So that's a separate, totally, you can be standalone probe, and people work on galaxy clustering. It's just finding the positions, correlations between the positions of the galaxies.
Gotcha.
What you can do is correlate the shapes of the galaxies. So shape, meaning if the galaxy has this shape, what is the probability I'm going to have the shape of the galaxy like this, and for the whole sample. And that probe is called cosmic shear.
Okay.
So that's really the weak lensing.
Okay. I see.
It's a bit different. What you can do also, you can combine. You can measure the shapes and the position combination. That's another probe.
I see.
It's called galaxy cluster, galaxy lensing, sorry. And what we do mostly now in cosmology, we can combine them. So this is 3 times 2-point correlation.
Right.
And we call it 3 times 2 points. 3 times 2 pt.
Right.
So that's also a probe. But then each of these probes have systematics assigned, or they come in with their own problems, right? They do bring something to the table when they're combined. And I say they usually, if you have what parameters, let me use a different color. If this is some parameter x and y in cosmology, you get these constraints like this. But then if you, let's say this is like one of the probes, but when you combine them together, it shrinks. It really, it helps constrain the parameters better. However, the galaxy clustering suffers from something called galaxy bias. And this is the bias towards our bias because we do not understand the distribution of dark matter the best. So you have to assign some sort of function, the galaxy bias function, to explain how your matter is distributed, because the light doesn't really follow the distribution of dark matter. The shapes of galaxies suffer from intrinsic alignments. Right? This is this subtle effect of the shapes of the galaxies that I mentioned. And on top of that, you have the fact that galaxies that are close together will be intrinsically aligned.
Yes.
So you have to account for that, right? You have to solve
And not
that.
random.
No, it's not random. Locally, it's not
Yeah.
random. So you have to find how to explain what is the curve, right? How, and of also, how does it change over time? Meaning, does it have a redshift evolution? And we do detect this intrinsic alignment signal, but only on certain types of galaxies. Only on red galaxies, what we call. Not so it's a very complicated effect. There is another thing that all of the galaxies suffer, but we don't understand, is the baryons. We call them baryonic effects or baryonic feedback, which is the small-scale physics that is coming to make your life miserable, because the feedback, so the gas of the locally, like in the galaxies, right in the clusters, these active galactic nuclei will eject the gas out of the galaxy and will change the whole structure dynamically. So, and we all know that, explaining or trying to model how gas behaves is very difficult. But you have to account for that, because now it matters, because we are not, just looking at the large chunk of the universe. Now our instruments are so powerful that we can zoom in.
Right, exactly.
Yeah, but then you have to explain what you're seeing.
Yeah. Right.
So
the more
it
local structure you probe, you have to explain whatever you see.
Yes.
Oh, that makes sense.
But it's challenging, and it can be really, it's a trade-off, as I said. Either you're going to discard a lot of data, which why would you do that? Because you have these fantastic instruments. But then on the other hand, you have to come up with a very good way of explaining physics on small scales. And the galaxy dynamics is extremely difficult. So, and we don't understand.
Nice.
You were mentioning these systematic effects. What are they?
Yeah, those are the intrinsic alignments of
those
galaxies.
are, I
yeah,
see,
those
okay.
are the we all just say systematics.
Ah, okay,
Yeah,
I
yeah,
see.
But those are, you can have the calibratable systematics, like stuff that actually is from the survey, it's just a selection of certain, like how, for example, photometric redshifts are actually bane of our existence. But it's also modeling there. Let's say multiplicative bias. I'm not going to use some words. It's basically stuff that comes from the telescope.
Right.
Or from the survey itself, the survey design. So how much are you covering? How much sky are you covering? I'm going to go back to the blackboard again. But if this is the full sky, neither of the telescopes we have so far that works in the cosmology realm, meaning the LSST, is not covering the full sky. And that's a problem.
Only patches, right?
Only patches, yes.
And that's why
there are
large
surveys.
samples help patching it better?
No, it's a different problem.
Okay.
So first of all, we have a problem in cosmology. Cosmology is very different from particle physics because we cannot repeat the experiment.
Yeah.
Right? We only have one universe, so we have one realization. So you're already hit by something called cosmological, like variance problem. It's a statistics problem, and I invite people to read about it. Secondly, our telescopes are designed the way that they simply cannot, at least LSST. It's positioned in the south hemisphere, right? And it will be able to capture about up to 18,000 square degrees, which is 40% of the sky or so. It is a huge patch of the sky. It's a nice footprint. We call it footprint, but still it's not the complete sky. And then on top of that, for example, going back to calibratable systematics, it's a fact that the survey, like LSST, it's a photometric survey. So you can do optical astronomy the way we do it in different techniques. One is photometry, where you have the imaging, like literally you see the image of a galaxy, or you can do the spectroscopy. So this is the DAISY, right? You don't get the image, you get the spectra.
Right.
So the point that is each of the probes or the techniques have their own pros and cons. So the pro of the spectroscopies is much more accurate, precise. Let me think which one it is. It's better in terms of accuracy. Or both, I guess. However, you cannot do, it's too expensive to do. You can't do full sky of that. It's simply too expensive.
I see.
Photometry, on the other hand, can do, in a very short amount of time, a large sample of the sky, but it's not as accurate because you're getting these bands, right, photometric bands. So you're getting pieces of information, and then you need to get your, for example, spectral energy distribution by getting, different parts of these bands, right, the photometric bands. And each of the telescopes, like LSST or Roman later, is going to have different bands. It's covering different parts of the spectrum, and then you need to infer the full picture from that. So it's less precise. So what we do, we calibrate our photometric sample with spectroscopic patches. So if this is a photometric survey that covers whatever, this part of the sky, of the full sky, then we would have, it's actually much smaller, much smaller, like tiny patches of spectroscopic sample, which we use to calibrate with.
I see.
And this is where you have problems like sample variances in affecting the redshift distribution estimate that comes from photometry, and a million other things. So there's actually a problem that we work on with a PhD here, where we are trying to improve the method of how this data is handled, right? Because you have, if you remember these L modes, right? You have a big L mode. Let me use this is a very cartoonish way of explaining it, but basically it captures the picture. If you have an L mode, you're only getting a piece of the information, right? Your smaller L modes, yes, but the bigger L modes are not captured by the calibration sample. So you are calibrating with something that is, it's not a full picture, but it's what we have right now. So we are trying to improve this method, and that will improve this redshift estimate. Redshift distribution, meaning the distribution of your galaxy sample.
Right.
And why is that important? That is one of the biggest causes of the errors or the uncertainty that we have, is just the fact that it is very difficult to determine the distance to a galaxy or any object in the sky. It's fine for the moon, something that's very close by, but we're talking about very, very big scales. So, and why is this important? Well, the distance to your galaxy and all of it, it's the lensing effects will be affected by it. People can look up something called lensing kernel, but that is actually, it is going directly into the power spectrum. The redshift of the object, or the redshift distribution itself. And then you have, so these are the calibratable. That is a very long answer to a simple question, but like you have to put the context there. And then the astrophysical systematics is all the physics. So it's not like related to the basically the limitation of the survey, the limitation of your instrument, but it is a limitation in our knowledge of physics. We cannot simply, I mean, people are working really hard on, getting the answers, but try to model gas or magnetic stuff, right? Magnetic fields, or when you start doing nonlinear physics, it is extremely difficult. What I mentioned 15 times already. But it's also choosing which model would be the best, because, of course, cosmology works in a way, and as any physics should, that its data is king.
It's vital, yeah.
So we cannot nobody's stopping you to come up with some weird theory, but if the data is telling you, no, this is how it is, then you have to look what is data telling you.
Right.
And what we do, I think at one point, I mentioned that I should talk about it, is the blinded analysis.
Yeah.
And so blinded analysis is something that is, I think is familiar to most people, because, for example, in medical sciences, they do blind tests, meaning if they're testing a new drug, they will distribute the drug and the placebo and test it on a certain amount of patients, and then,
Oh, interesting.
it's a blind test.
Yeah.
Or if you want to, I don't know, hiring someone, right? It's very blank CV, there is no personal data, it's just the work, right? So
Right.
you're blinding yourself, because all of us are biased. Even if you think you're the most open-minded,
You're still
liberal, there are always biases. You cannot. It's a psychological thing.
Yes.
It's not a physics. So
Yeah.
nobody,
true.
just because we work in physics doesn't mean that we're immune to these things. So in order to prevent yourself from being biased, and there's many, this is also a bias, right? Because we simply cannot observe the whole universe, or, when we have one universe, it's all types of biases. In order to be as careful as we can, physics experiments, usually, most of them, try to do blinded analysis. And it's much easier in particle physics, because they can blind most of the data. They can just test their infrastructure on, the synthetic or a small piece of the detector, and then not include it. And later, when they are ready to run the analysis, it's literally really pressing the button if everything works well.
Right.
And then you put in the real data, and then I've been very lucky to witness one of the unblindings.
Oh.
It was everyone who ever worked on the experiments tuned in, and we were watching it live.
Oh,
Wow.
nice.
Yeah. The way in cosmology now, it's a bit different technique. Because we don't have signal in a way that is like an event. You work in particle physics, so you know that. Sorry, that I think I have chalk on my face.
No, you don't.
Really good. In particle physics, the way they do is they do have events. So that's why usually they do frequentist
Right.
approach. And not only that they can repeat the experiment, but it's event by event.
Right.
We don't have event. For us, it's more like a distribution of everything. It's very smooth. And we have the spectra. So usually cosmology is very Bayesian in terms of techniques and statistics, or the way data is handled. And the way we blind is we have to agree on analysis choices before we do analysis.
I see.
So those are your credences.
Yeah, this is what we're gonna do. We're gonna start with a prior belief, right? It's a prior belief. You say, I think we should go with the lambda CDM
Yeah.
with whatever simple baryon model or no baryons. We're not gonna account for baryons.
Okay.
What are we gonna do about intrinsic alignment? Something simple, NLA model. We're gonna go with where we said lambda CDM, so W no WA, simple stuff, no curvature. We're gonna choose these things, and you set your pipeline for these parameters, and then you run the data with data assumption, and then you will say where your data is showing. How much is differing, assuming that this is the underlying truth, assuming that these are the assumptions about how universe is.
Yeah.
And every time, so if it proves that we are not there, like the data is moving a little bit to some corner like we saw in DAISY, right?
Yeah.
What you can do in the next run, next experiment, or the next run of your experiment, you can correct your prior beliefs.
Right.
So, for example, cooking is a Bayesian process, and I heard it somewhere. I cannot quote you where, but it's a very good explanation. So, for example, you making let's do ramen because I really love ramen. You're making ramen yourself, and you have a prior belief that it needs some salt.
Right.
But you're gonna taste it, and then you will determine, okay, I need more salt, and then you're gonna add more salt. So basically, when you do another analysis, so we thought that this parameter was this. We know the central value, but we also put priors, the how much we're gonna allow our walkers when we do the sampling
Right.
to go, because, and it's completely okay, because we know that, whoever you ask on the street, they know that, moon is not 10 kilometers away from here, right? So you already have some prior knowledge, so you constantly can build upon that. This is why it's important to have these experiments, to combine them together, because even if you don't get the major science news result, every time you learn a little bit.
Right.
And it all, all the pieces
Absolutely.
matter, yes.
I was actually going to go on a tangent, but I think we
No,
should
that's
ask
fine.
the DESI question.
Oh yeah, of
because
course.
she mentioned,
Yes. So So I mean, we all saw how big of a headline it created, the new DESI results. So it also talks about how this lambda may be varying with time. What are your thoughts on that?
Yes, so it's really good follow-up from what I just said.
Yeah.
So you start your analysis, your data analysis. So all the data is calibrated, all the catalogs are done, your infrastructure pipeline where the data is going to be run through is fine. You need to, press enter for cosmology. In ideal world, of course, it's much more complicated and stressful than that. However, let's assume it works like that.
Yeah.
But as I said, you need to have frozen analysis choices. So for example, DESI said, okay, we're going to assume lambda CDM. Let's say the W naught is a -1, right? Is the crosshairs at -1, and these equations just tell you the evolution of the dark energy over redshift over evolution of the universe, right? So if you assume lambda CDM, they say this is how they started doing the analysis. They assumed, okay, this is the story. This is what we think is true. But then the data was pushed where? It's pushed this way, sorry.
Yeah.
Right.
So away from the lambda CDM.
Yeah.
So these tiny little differences, or the tiny little subtleties, can tell you a lot. But the point is, now you have to interpret it. And it can be many things. So what you can do, as we do in all the collaborations, you have the forecast where you can play around without any data, real data. I mean, we do have the synthetic data, just the theoretical vectors. And you try to tune in us, okay, if I, for example, if I include baryons, and crank up a certain dial, will this move this way or that way?
Okay.
So you need to test all the models, and then that will help you determine which model you're going to go with. But even if you go, it doesn't matter, you can always assume lambda CDM, but then the data will tell you something, and then you can interpret because you know what caused it. I mean, it can be many things, right? Because each of the systematics is affecting the power spectrum, and then later on it translates into these contours in different ways.
I see.
And of course, these effects are not separate from each other. They're degenerate between themselves. So basically, it is like you think about some sort of path over the water, like the stones on the water, but it's not like you step on one stone and not other ones are not affected by it. Actually,
Right.
some systematics are connected, and we are trying to understand how degenerate they are, and how to break the degeneracies, because
Oh.
then you can figure out what caused the push. You know, is it coming from the redshift estimate? Is it coming from baryons? Is it coming from intrinsic alignments? What is moving the contour for whichever combination of parameters we're looking
Right.
at?
I see. So there's no consensus as to what exactly is causing this shift. We're still is that still up for grabs?
Everyone has, I don't know, like I don't work in DESI, so I don't know what they, I mean, I listen to talks, you can find their interpretation, but it's too early to say.
Okay.
What I would do, what I really try to do, is there is a lot of code, and I'm not talking about DESI, as I said, I don't know, I don't work in that collaboration, I heard nothing but great things, they're wonderful people, but in general in science we code a lot, and astronomers are not the best. There are fantastic people, but it is a lot of things are it's a mess. It can be done much better.
Okay.
So some of the people, like I'm very, very much into standards and trying to learn from, people who work in software how to handle it best. So we can be talking about, fancy physics or new physics, but maybe this push, not in DESI, I'm not saying about DESI, but maybe we're seeing something because we're not all using the same parameters, because, maybe you're running your script in something and then there's 0.034 I might be using, and if we're not consistent, these tiny things propagate. Those are tiny effects, and the power spectrum, plus you have, of course, the numerical, limitations of computers.
Of course.
So you have to be very, very careful. And the power spectrum very sensitive to minor,
It amplifies.
Yeah, but you're doing the transforms and everything. So first, I would make sure that everything is, and this is what we are trying to do, consistent. Everyone uses the same thing. It can't be like I'm checking one thing, you're checking the other, but we're using completely different cosmology, for example. What if, there's a tiny difference in your parameters? These things really matter.
That's true.
So once that is cleared out, and we are 100% sure that nobody is, everyone's on the same page, then we can really see, okay, of course, I'm not saying that I'm only doing that. This is why we're meeting in 2 weeks here at Duke to work on intrinsic alignments and then learning how to best tackle this very difficult systematic. So we're tackling it from simulation side, from observational, theoretical, and it is not one collaboration. It is literally everyone who works on that thing in every collaboration, and theoreticians as well. They will come here and we're going to have a blast.
I'm sure it's going to be a blast. Okay, so moving on, I'll go on a slight tangent. Are you also keeping up with some other approaches? So, for example, there are approaches that want to completely exclude dark matter and dark energy, and are more focused on modifying gravity, and they've had some success in fitting gravitational rotation curves and so on. And do you think these models are still viable, or they're just shooting in the dark at this point?
Well, there's many classes of these theories, right? There's a lot of now everyone who has an access to an AI, ChatGPT suddenly understands physics, which I think is without any training. So we're not talking about that, but exploring different ways of explaining gravity is absolutely welcomed by the community, and we actually have certain working groups that are working on that, and I have a project with Bastien, who sits in an office across mine, where we're gonna also tackle something like that with this technique and
interesting.
whatever we can
Very cool.
combine. But it's not just us. A lot of people are working on it, and they are gladly exploring other possibilities.
Wow, that's interesting.
It's just that it cannot be complete rubbish.
Yeah.
It has to be physics,
No,
right?
absolutely. Yeah.
So people are absolutely working on it. It is absolutely not true that we're only trying to,
Yeah. So there are also other candidates for, if you talk about dark matter, we have WIMPs, we have neutrinos. What, according to you, should have the greatest bet, if either of them or if something other than these? What do you think is the best candidate for dark matter?
I think at this point now, I stopped thinking about dark matter in terms of phenomenological or like a model.
Okay.
Because it's just the way I do work now. I don't really think about the nature of it in that sense. I mean, of course, it will tell you the nature, how it correlates to some other components or the parameters of cosmology, but from the point of view of which model, like is it a WIMP, is it an axion, is it a, I don't really think about it that way. It's just the way I'm doing work now. I did, care when I worked at Xenon collaboration. Then, of course, it was a WIMP because that's what the design of the detector is, to detect WIMPs if they exist. But I don't, that is not really, maybe at some point, we do have people within our collaboration who are theoreticians who are trying to plug in the models they developed into our machinery, meaning the theoretical predictions that we can do, meaning you can calculate it very easily on your computer and it spit out your power spectra or whatever you want to do, but with some axion models. For example, Keir Rogers works on axions and he has models that he's going to plug in. So yeah, but I don't have a personal preference for a model. For me, whatever data tells me. But as I said, I cannot really provide an answer to, it's a WIMP.
Right.
It's just simply not the shopping list of what I am working on, yeah.
That's fair. That's interesting. We can move on to the tail end of the podcast, where at the Nomads podcast, we really want to highlight stories and journeys of physicists. We really want you to share some highlights of your journey as a physicist, how you got into physics, and what led to this postdoc position here at Duke, and highlights along the way.
Okay, so my path is very nonlinear, very, very nonlinear. I didn't dream of becoming a physicist ever. Okay. I was not into science. I was just a good student, and I was into art a lot.
Oh, wow.
And then I don't even know how it happened. Oh, yeah, I didn't know what to do after high school. I wanted to do art, but my parents were against that. So I was forced to just, do whatever, university or college, and I ended up in some college that wasn't for me. And I really didn't go to classes except physics. I do not understand why. To this day, I cannot explain to you why. Because it was, I was just going out every night, enjoying the scene, the club scene, or the metal scene.
Metal scene. Oh, wow. You're a metal fan.
Oh, yes.
Oh, I'm a metal fan.
Yes.
Oh, wow.
Absolutely, yes. Yes.
What's your favorite metal band?
Metal band, but I really like Dothimsgar. It's a black metal band from Norway.
Yeah.
And I know them personally.
Yeah. Oh, wow.
Oh, wow.
Oh, really?
Yeah.
That is so cool.
Awesome.
That is so cool.
Wow.
They're one of the the old crew from the 90s. And
yeah. Oh, wow. Yeah, my favorite band is Opeth from Stockholm, Sweden.
Love Opeth. Oh my God, I'm gonna look. I love. That's the Blackwater Park album.
Yes,
I really like that album.
One of
It's
the greatest
fantastic.
albums.
Yes.
Yeah.
Oh my God, amazing.
Okay, metal scenes.
Metal scene. Yeah. No, I was just going out, and it was really a lot of personal stuff that was going on that I would not like to share now, but it was just a way out for me to finally live, and but then, which is normal, right, in teenage years or whatever, late teens. But for some reason, I would go to these classes early in the morning, physics. And I think what I was studying was some sort of graphic design. I mean, it was not what I wanted to do. And then the teacher there, physics lecturer, she asked me to her office and asked me, literally, I will never forget these words, "What are you doing here?" And I said, "I don't know." And then she said, have you ever considered doing physics? Like, you know, when it was never on your radar, I never, you know, was fascinated by what, I just had a different upbringing and life before. So I disregarded that, but it stuck with me is when somebody really looks at you and in a very positive way, because she saw that I understood. I was a very good student, but I mean, up to this college. But it was just like I couldn't find myself. It was really the personal stuff that was affecting me. But yeah, I disregarded it up to a point where I really, you know, going to fail a year because I was absolutely not in classes except this physics. And then, well, my mom was really angry with me, and she said, you know, you have another chance, like, you know, either choose a university or, you know, you need to go and work. You know, work, whatever.
Right.
And then I said, as a revolt or whatever, it's like, I'm going to do physics. And she was like, okay, this is, you know, completely out of the blue. But then I did it. I mean, there was an entrance exam, and I didn't prepare at all for that. But it was very easy to get in. And then I chose astronomy because there were several like modules you can choose, and you can do just general physics or I don't know what I had. And I liked astronomy, not because of astronomy, but they had, I remember on the list of like a curricula, at some point in the second, third year of classes, it was general and special relativity, like two separate courses. It's like, I don't know anything about that, I'm going to choose this. Wow. And so I got into physics, and I had no clue where I was. Like, I was completely, you know, lost in a way, but it was fun. You know, people, was very few of us. But then there were a lot of political problems that are still present because I was doing undergrad in Serbia. I don't know if you follow the news, but you can look at it now and what is going on in Serbia for the last 30 years. But if it affected me, the level of corruption. So my undergrad lasted a very long time, not just mine, everyone, because of the corruption, and we couldn't get out. Yeah. But in the end, and so this is one part of the problem. And then another part of the problem is also, which you don't have money. You know, it's a poor country, and it is difficult. And then I also wasn't getting into it. Like, first 2 years, it was like, okay, but, you know, it takes time for, I guess, the knowledge to, maybe to, you know, slowly start to go into your head in a way. But I had this moment. I had a moment I will never forget, and I know it sounds absolutely melodramatic, but it's absolutely like, this is how it happened. So it was third year of physics, and we had lab work for the nuclear physics course with a very special professor. I love that guy. He was fantastic. But I was with my best friend at the time, and two of us, we were, oh my God, we were the worst. Like, you know, we came into this lab to do the course with, you know, like food, and he was like, get out. You know, like, we were completely very young. But in the end, at this particular time, we were doing an experiment, really nicely ties with this. The experiment was called statistical fluctuations, and this is a very simple experiment in physics, in nuclear physics, where you have the radioactive source, and you have some sort of counter. In our case, it was a Geiger counter. And what you do is you set up your experiment, and then you say, okay, I'm going to measure how many counts I have per minute, and I'm going to do that many times. And in this particular detector, one count means one radioactive decay. It doesn't tell you the nature. It just tells you there was a decay or not, right? So I don't know, like in a mid you have 1,500 this time. And then it was really a state of complete frenzy with two of us, completely, you know, talking about music or talking about what we watched the movies. And we were terrible. But during this time, and he made us do the experiment, not like there was no laptops or anything. I mean, it was back in the day. And we were doing it on a millimeter paper with pen, you know, and every time you see a count, so you say, like, you write down on the x-axis, you're building a histogram, right? So you say, oh, I don't know, 1,500 counts, whatever, 1,600 counts, and so on. And every time you just put a tick.
Mm-hmm.
Yeah.
And during this whole crazy thing, I'm doing these ticks, and I'm building a Poisson distribution. And it was right in front of your eyes, and it was really some sort of moment for me, like, of realization that I'm doing a very profound thing in, measuring something in nature, a very, statistical, the Poisson distribution, with very simple setup, and like, I'm going to do this. Like, I want to do this for the rest of my
That's
life.
beautiful.
It was really, really deeply, I will never forget that, really. And also what I really liked during my undergrad time is writing up reports. Like, it was just like, when you do the lab stuff, right, you need to write the theoretical introduction. So it's a mini paper, right? Of course, you're doing physics that was already done,
Yeah.
but you're learning how to do that. I really like that. I like organizing things because, like some of us in physics, that we do have some sort of neurodivergency. I like organized things, and I like this a nice order when you collect the data, this process or the whole scientific method. I like from collecting the data and then processing it, analyzing it, and interpreting it. It's fantastic, and to this day I really like writing. So this was the undergrad, and this is, as I said, in the third year, and you can see by my grades, it was like at the beginning first, and then it was right. No, it was really, I don't know, something changed in me.
Wow.
Because I guess I was already, it was done. I was done with, being crazy. But then it took some time to, how to get out and out of the situation there, where the country where you're studying is not supporting you, and it was very difficult. It was for all of my colleagues, all of us. It took a very, very long time to finish a 4-year undergrad because of the problems, and you don't have country, have the legal system that is in place, that is enforced to protect you and prevent stuff like that happening. In the end, the salvation for me came in the shape of a full scholarship and tuition from the European Union. So there was a program within the European Commission called Erasmus Mundus, I think you know. This is where you have the exchange students, so you can do masters outside of your country. And there was a special program called Astra Mundus, where it was a collaboration between the universities of Innsbruck, Padova, Tor Vergata in Rome, Göttingen in Germany. I said Innsbruck, and then was University of Belgrade. I was at University of Novi Sad in Serbia, by the way. And it was also, there was another year I got the offer, but I got the full tuition, but not the scholarship. And because my family is poor, they could not afford me living in Europe for 2 years. There's simply no way. So I had to decline.
Oh.
And then I applied next year, and I got the full thing.
Wow.
Oh, wow.
Okay.
So that means that European Union paid for my tuition for 2 years, and I was getting salary for 2 years.
Wow.
To study astrophysics. It's an international program. It was 12 of us, I think, in my year or something like that. So I studied my master's. It was 2-year master's. I was in Innsbruck, Padova, and Göttingen. That was really lovely. I mean, it was very, very difficult. All of us, I think, cried at some point from the stress, because it was 3 countries, right? You were just running around, and it was a lot of, I had 21 exams in 3 semesters, and then the thesis later. It was really crazy. And it's different countries, right? Every country has different system, but it was everyone was so lovely. Like, everyone was so welcoming. I don't know if I loved the Italians more on the Austrians and in Germany. And it was the first time I really felt the taste of how real research looks like. But it was only, because he's still studying, and as you should, because I don't think you can actually do as quality research at some younger stage. You need to build a foundation.
Yeah.
You need
For
to
sure,
understand the physics and mathematics
Yeah.
and the code, of course. And then I got a PhD, and I started doing PhD in Germany at University of Freiburg
Mm-hmm.
within a xenon experiment.
Oh, okay.
And I was there for 2 years, and then I had problems, especially personal problems,
Mm-hmm.
personal tragedy. I had to quit.
Oh.
Maybe I will talk about it more at some point in my life, but not now.
Okay.
It's
Mhm.
also because of the legal stuff.
Oh.
Yeah, no problem.
I can tell you when the camera's
Okay.
Okay.
and but I had to quit, and I didn't know what to do because this personal tragedy I had to deal with. It was terrible, and but like I have no job. I don't know what to do. And then a professor from Switzerland,
Mm-hmm.
she contacted me and said that she thinks that I should stay in academia because she knows my work from Xenon,
Mm-hmm.
and that she would recommend me. And immediately, I applied for a PhD position in Newcastle, and I was really choosing a place where a woman was
Mm.
a supervisor. I wanted to work with a woman,
Mm-hmm.
absolutely.
Right.
And I got so lucky. So I was chosen to do a PhD in Newcastle in the UK. Of course, the move there was terrible because it was COVID time. So
Oh.
trying to move from Germany to the UK during COVID, it was
This was around.
2020. Yeah.
Yes,
20.
that's when we left the UK.
This is when you left.
Yeah.
But yeah, I literally sailed into Newcastle. We took a boat because there was no other way. It was,
Oh,
and also
right.
Brexit was coming. So
Oh,
it
yes,
was,
yes.
it was terrible.
Yeah.
But yeah, we moved, and I had the most wonderful experience in Newcastle working with Danielle Leonard and Joshan there. It was absolutely great. To
That's
this
good.
day, I still, especially with Joshan now, it was my second supervisor now, I still work with him. They were so nice to me, and it was,
Wow.
this is when I realized it's, okay, you love physics, we all love physics, science is very, very interesting, and once you get into it,
Mm-hmm.
and you feel the love,
Yeah.
this is why I work over the weekends, because I love working on it.
Right.
But it can be the best thing ever in physics.
Mhm.
You can work on the topic you really like. For example, you like QCD, you like theoretical physics, you like particle or nuclear physics. But if your supervisor or the people around you are not, you're not connecting, or there is some abuse going on, you will not have a good time.
Absolutely.
So
yeah.
this is
That's
why I
so
always
true.
put emphasis, and this is why I am thriving at Duke, because the supervisor, my supervisor here is Michael Troxel, and I haven't, of course, this is now a different person. I am not comparing to Danielle, but now I have a absolutely full trust and support from him. I've been here for 8 months now. I mean, we know each other from before. I have never been more supported in my life than here at Duke.
Wow.
Absolutely love it here. I would like to stay here forever if I could. Yeah, I really, really think that is, it's not really, of course, money matters, right? If you have enough funding to go places, to work with other people, because this is where the magic happens. When it's not really during the classes, is when we are, during the coffee breaks, it's like, have you ever thought about this? Yeah, or people approach you, which happens a lot actually. It's like, oh, Niko, can I talk to you? It's like, what do you think about this? Can we do maybe? And then 3 hours later, you're covered in chalk, and oh yeah, we can try to do this. I don't know, let's see. You can't do this if you don't have the money to go places. So that is very important to support scientists, because this is where as I said, the magic happens.
Absolutely.
But if your people you work with, you all treat each other well. So there is really no distinction between, who's faculty, who's staff, who's the undergrad. All of these people are valuable, all of these wonderful, young people that I get to learn from, and they learn from me, and we learn from Troxel. It's all, it's really, it's like a tiny family where we're all just having fun, making plots and trying to figure out how to do stuff.
That's very
That
nice.
feeling is the best.
Wow.
So
Absolutely.
the supportive environment, the crucial thing. If you
100%.
work in an environment where people are backstabbing each other and the boss is allowing that,
Absolutely. No, agree.
Absolutely.
Absolutely agree.
Yeah.
Yeah.
So you're also a woman in STEM, and I would like you to talk about how that has transitioned over all these years as an undergrad, as a master's student, and PhD, and now postdoc. And what advice do you have for young women physicists, especially?
Okay. As it can be difficult, it doesn't matter. I realize, and I talk to senior women who are very famous in the field. There is still there. So the point is that there will always be terrible people.
Mm-hmm.
The point that if so let's try again. You can edit this out. I'm just trying to phrase it in a different way. There will always be terrible people in any workplace, regardless of their vocation. If they have 3 PhDs, physicists are not immune to that. I always say physicists are just people with jobs, right, and a diploma.
Absolutely.
What makes difference is if you work in a place where there is a clear code of conduct that is enforced, or the policy. That means locally at your institution or in a collaboration you work, if people are misbehaving towards each other, especially towards women or minorities and doing these horrible things, if this is glanced over and if you let it, happen, it will pick up. And if the collaboration, as I said, the institution or your group have very clear policies that I said enforce. It's not like, it's code of conduct is some sort of piece of paper we wrote at some point or copied from somewhere and it's just there performing. No, these things have to be enforced. And that can be some serious stuff like, sexual harassment or those really, really bad things. But it can be very subtle things that should not be glanced over.
100%.
For example, let's say we're in a group meeting and it's a mix of people of different academic ranks. There should never be a case where an undergrad, so somebody who has less power, should be afraid to say, I don't understand this, or he can say, you should not talk to me like that. I don't like this. They should be okay to say, it doesn't matter who, if somebody, if it's a faculty, if some sort of professor, I don't care. You need to be able to speak up. If it's something very serious, there should be a body that is handling this situation. So as a PhD, if somebody is abusing you, that means that your supervisor is not doing a good job.
Absolutely.
There should be a body where you can confidently go and tell, pour your heart out, because these are very difficult situations. And in academia, it is a very nefarious, because you're constantly, you constantly think that you're stupid if you are, but it's not that. People need to understand that, your intelligence, your capability, your skill in physics is completely different from, how you're treated. And basically, the supervisor's role is not to have an assembly line of people that push out, get diplomas every year. Each of these people that work in an institution is an individual, it's a human being. It should be, approached in a different way. So that means being a supervisor is a very difficult job, right? You need to understand that, you cannot talk to one student you cannot talk to every student in different ways. You need to adapt yourself because everyone works in different ways, right? So you have to make sure that this person is thriving in your institute.
Yeah, absolutely.
But if you step over the line and you cannot, for example, I work all the time because I like working. I cannot absolutely expect that of my students, and I could never ever ask and be yelling at them, or these sort of things are absolutely unacceptable. But if I would yell at someone, I'm sure that the Duke here would provide immediately. Somebody would report me, and I would have a very long and difficult conversation with my boss, as I should, because I should not be behaving that way. So the body there has to be certain parts or the, I don't know how to call them, certain ways or channels where a student or the affected party, I mean, it can be a professor as well that's affected, they can go certain routes in order to solve the problem. The first to address it, to acknowledge it, because most of the time, and I've heard very big horror stories, and I suffered myself, you have nowhere to go to. And nobody believes you for some reason because you are, I don't know, a woman or an undergrad or a PhD, and there is, an authoritative man there.
Absolutely.
Right.
With a track record, but as full power, no one should have absolute power. This is not total. This is an institute. Of course, we have the, universities should have autonomy, but still, these things, and what students need to know, especially women, if you're in a situation where you are endangered in any sort of way, first try to find the channels to talk. Do not go on social media immediately, try to find some legal ways, or the protocols, check what your institution or the collaboration is offering. Because in most countries, in developed countries, there are bodies like that. There should be. And always write like a written record of these things, and never ever just leave. There should be a written record of somebody else's horrible behavior, because maybe it did not work for you, maybe you had to go, but if there is another person starts complaining, because these people are usually, they do it in series. It's not like there is a pattern.
Right.
So then some, bodies of the university will be able to track it down as like, okay, this has been happening. You need to go. Like you have no place here in this community. So these sort of things. Another thing that I've noticed as a woman in physics, and as I said, doesn't matter your rank, your accomplishments. It's very subtle, but it absolutely it frustrates me so much. I would curse now, but we're not going to curse in the podcast. If you know something and you say something, you think, you have discussion with a group of people. Women have to repeat their stuff and try to explain themselves many times compared to men. Men, they say something and everyone just nods, yeah, like a good idea. Whereas women have to, I did it. And then they question, they constantly questioned. And this comes from men who are actually, in their minds, they're very open-minded. They're very, but those things are noticed. And it's,
and then you start to doubt yourself whether you're saying something right or am I not clear?
I want to go because, as I said, I am very nice to people. I try to really, make everyone feel welcome. But at some point, I really want to just curse and because you are really pushed to the limit. Like, aren't you listening? This is what I said. I had a few years ago, I don't know, it was somewhere in a very famous place, and then I was shut down by a very big name, and then another guy had to come in to defend me, and once he said, like, well, I agree with Niko, I was like, and then immediately, oh yeah.
Oh God, that sucks.
I will never forget that. This is frustrating, and I think that, men need to realize that in the community, and I don't think that they are welcome to, they are open to that, because nobody thinks that they are
in the wrong.
As I said, but we all have biases. I know I have biases, and I mean, this is why you need to have friends in your life who will tell you, or your partner. This is why I really love my boyfriend will point out to me, like, you should correct that, right? This is, and then it doesn't feel good, right? But you have to acknowledge it, and because what's the point of this life, right? Make this world a better place.
Absolutely.
And you can do that by changing yourself and understanding your patterns, and a little bit of a life talk at the end.
That was beautiful.
Well, we hope through this podcast, all of these things get amplified, and people notice these subtle things that go on unnoticed, and and how women in science actually feel about that. On that note, Dr. Niko, thank you very much for doing this.
Thank you for having me. Thank you.
This was wonderful.
Thank you.